let's get into our question. Our question states that we have a 3-meter long pipe that is closed at the top end. That pipe is slowly pushed into the water until the top level of that pipe is level with the surface of the water, and it's asking us what's the length of L. So this L right here. So our process is we're going to use Boyle's law to find the length. Boyle's law is this equation right here, and we're using this because it states at constant temperature, because this environment doesn't change in temperature, the volume of a given mass of a dry gas is inversely proportional to the pressure. And like if we look at the equation straightforward, we don't have L to find the length, but if you notice, once we start plugging in how we're going to calculate each variable, we do have the L values. But as a spoiler, we're going to have to use the quadratic equation to find roots to be able to find what the length is, because it's going to be hard for us to isolate the L in itself. So we'll get into the specifics of that when we get to the calculations, but for now let's start with Boyle's law. And to plug in each part, we know that the initial pressure is just atmospheric pressure because it's outside of the water. So that's why we have P0 right here, multiplied by our V, which is our cross-sectional area as A, multiplied by our length. And our initial length is 3 meters as stated right here. So that's going to equal the pressure once we push it into the water, which is going to be our atmospheric pressure, plus this right here, which is going to be the extra pressure when you push it into the water, which is the density of water multiplied by gravity multiplied by the length, and then again multiplied by the volume at the end, which would be this cross-sectional area multiplied by the length at the end, which we do not know. So we can see that we can cross out the a's here since everything's being multiplied, and you'll just end up with this right here. You move the L into the parentheses and you'll end up with this, with atmospheric pressure times L plus density times gravity times L squared. And then we can make this into a quadratic equation by moving everything to one side. So I just moved everything to this side right here. So I subtracted this side and we end up with this equation right here. And then this looks kind of ugly right now, but this does represent a quadratic equation. I underlined each part to a specific color so we can kind of see this a lot easier. So the A variable, the quadratic equation, is density and gravity. The B is atmospheric pressure, and then C is atmospheric pressure times 3, or negative atmospheric pressure. Make sure you don't forget the negative. And then we're going to plug these into the quadratic equation to find roots to find our L. So we're gonna get this when we plug in our A, B, and C to the respective parts. And now we're just left with this. So we can't solve L straightforward because we don't have the numbers for atmospheric pressure, density of water, or gravity, but since this is usually common knowledge, we can Google it. So our atmospheric pressure is 101,325 pascals. Gravity is 9.8 meters per second squared. And then the density of water is 1,000 kilograms per meters cubed. So once we plug those in, we'll get this big calculation right here, which will leave us with negative 12.77 meters and 2.43 meters. And in this case, since we can't have negative lengths, we could just discard this and we'll just be left with 2.43 meters. And 2.43 meters is our answer, and it's this length right here when we push it in the water.